All right, so let's finish chapter 5. We discussed chapter 5.9 and section 5.10. Okay. Okay, let me share the screen with you. All right, okay, so 5.9 is prediction intervals and tolerance levels. Okay, so far in chapter 5, we all discussed CI, or confidence interval. Okay, so what is prediction intervals and what is tolerance levels? So confidence interval for a parameter such as population mean, or difference between two means, or difference between two proportions is an interval that is likely to contain the true value of the parameters such as the population mean. Okay. So this is different from prediction and tolerance intervals because they are concerned with population itself, okay, and with values that may be samples in the future. Okay. And the method presented here are valid only when the population is known to be normal. Okay, so remember that. So if the population is not normal, we cannot use the equation discussed in these sections to get the prediction intervals and tolerance levels. All right, so prediction intervals. So prediction interval is an interval that is likely to contain the value of item sampled from population at a future time. Okay, so when it is a future time, we should change the range of the interval a little bit. So basically increase the interval a little bit, as we can see from here. So if x1, x2, xn is a sample from a normal population, okay, again, this is one of the prerequisite requirement. So normal population, and y is another item to be sampled from its population whose value has not been observed. Okay, this is y is a future value. And then for any prediction interval for y, we use this equation. Okay, this is sample mean value of x. T is again student's t distribution. The degree of freedom is n minus 1, as we can see from here, and the half alpha does not change. Okay, S is the sample standard deviation, and n is the sample size. Okay, so the probability here, because this is a future value, we can say it is a probability. Okay, so the probability is n minus alpha that the value of y will be contained in this interval. So here is the example. We have sample of 10 concrete blocks manufacturing a certain process has a mean compressive strength of 1312 megapascal. Okay, so this is not realistic value. This is too high. For normal concrete, the strength is around 30 to 50 megapascal. But this is stronger than steel. But anyhow, this is not concrete class. So with sample standard deviation of 25 megapascal, okay, asking for 95% prediction interval. Okay, so asking for prediction interval, we just use the equation in section 5.9. Okay, so prediction interval for the strength of the block whose strength has yet to be measured. Okay, so first of all, we can calculate the parameters, because this is 95 prediction interval, so 95 equal to 101 minus alpha. So half alpha will be 0.025. So the t-value n minus 1 alpha will equal to n is 10 minus 1, 0.025. Okay, so from table 8.3, we can get this value, 2.262. This is, again, use the table 8.3. Okay, so then based on the equation, t-value 2.262 s plus. Okay, so here n is 10, sample standard deviation 25, sample mean is 1312. Okay, so we can calculate the prediction interval. And in this slide shows the difference between prediction interval and confidence interval. Okay, and we can see the only difference between the prediction and the confidence intervals from the calculation standpoint is the 1. Okay, remember this is S1 plus 1 over n. Okay, so versus S times 1 over n. Okay, so only difference is the 1 here. Okay, so this one make the prediction interval much wider than its corresponding confidence interval. Okay, the reason is simple, because this is a future value, and for future value, we always have uncertainty. So that means we need to increase the interval by introduce this one. Okay. Similar to confidence interval, we also have one-sided prediction interval. Sometimes we only care about the upper level and also all the lower level. Okay, it's similar. Okay, but we also need to require the population follow a normal distribution. Okay. And here shows the equation for one-sided prediction interval. For any boundary alpha, for upper bound, we choose plus, still the t minus 1, but here is alpha, it's not half alpha. Okay. Remaining will be the same. For the lower bound, we use minus instead of plus. Remaining will be the same, so degree of freedom is n minus 1. This is again alpha, not half alpha. Okay. So that is prediction interval. Tolerance intervals for a normal population. Okay. So let's look at the equation for tolerance interval. It is defined as interval that is likely to contain a specific proportion of the population. So what is proportion? How many percentage of the population that interval can contain? So we call that tolerance interval. The requirement for tolerance interval, the equation is still the population has to be a normal distribution. Okay. So if x1, x2, xn is a sample from a normal population, the tolerance interval for containing this percentage, this proportion of the population with that confidence level is given by this equation. Okay, so this is sample mean value. This is sample standard deviation, nothing new. But here is a new parameters. Okay. So this key value, we're gonna use another table, is table 8.4. As we can see, the key value has 3 parameters, the n, the alpha, and the gamma. Okay, so let's look at what does this n, alpha, and gamma mean. The n is the sample size. The n is the sample size. Okay, so alpha is the confidence interval alpha here. Okay, and gamma is the value here. So depending on what proportion, what percentage the interval is carried by the population. So the gamma is here. Right. So in this example, the lengths of bolts manufactured by a certain process are known to be normally distributed. Okay, so before we use tolerance interval, let's look at where the question tells us it is normally distributed. If it's not, we cannot use the equation. Okay, so normally distributed, so we can use the equation in previous slides. Sample size is 30, so that is n. The average length is 10.25. Okay, so that is the mean value of fx. Standard deviation of 0.2. Okay, so that is s. So find a tolerance interval that includes 90% length of the bolt with 95% confidence. Okay, so what we need to do is we find the key value, kn, alpha, and gamma. Okay, so n is 30, is the sample size. Alpha is based on the degree of tolerance level, confidence level. Okay, so alpha will be 0.05. Okay, because tells us 95% confidence. Okay, so use this equation, 95 equal to this, so alpha is 0.05. Okay, so alpha is 0.05, and gamma is depending on how much percentage of the length of the bolts. Okay, gamma is 0.1 because tells us it is include 90% of the length. Okay, so 90% is equal 90, so alpha will equal to 0.1. Okay, so this key value, key 30, 0.05, and 0.1. So let's go to table 8.4. That's the new table. It's here. 8.6, 8.4 is here. Okay, the key value is 30. So the sample size in the first column is sample size n. So you look at some number 30. 30 is here. Okay, the confidence level. Right. So this is 95%. You can show here confidence level 95%. Percentage of population content is 90%. So from here, actually, it's the second column of this table. So the value from here we can see is 2.1398. 2.1398. Okay, this is how we use the table 8.4. Okay, so the key value from table 8.4 is 2.1398. Sorry, 98. So table 4. So the tolerance interval okay, so use this equation. So x 10.25 plus or minus 2.139 times s 2.2. So that is tolerance interval. All right. So last section in chapter 5 is 5.10. There's no equation showed here. Just showed us how we can use software, use simulation to construct a confidence interval. Okay. So if x1, x2, and xn are independent random variables and with different standard deviation, okay, sigma 1, sigma 2, sigma n, and if u is a function of x1, x2, and xn, so u is a function of that, okay, most of the case, u will also follow a normal distribution, most of the case, but it's not always, but most likely. Okay, so we can use software, use simulation to determine if u has follow a normal distribution or not. Okay, so for example, in a simulation, we can generate hundreds or even thousands of x from a normal distribution based on parameters such as sigma. Okay, and then the software will transfer the x value into u's. Okay, so based on the function, because u is a function of x1 to xn, okay, and then we get thousands of value of u, and then we can check if u are normally distributed or not. Okay, so that's the idea for using simulation, to use simulation to check. So we have finished chapter 5. So in this chapter, we discussed many sections. Okay, we learn about confidence interval, most likely, except for section 5.9, we discussed tolerance interval and other prediction interval. But mostly we discuss confidence interval. So depending on situation, if it's large sample or small sample, if it's question is asking for the mean or the proportions or the difference between the means, okay, so we have different set of equations. Okay, so the tricky part is we have so many equations, but how we zoom in to determine which set of equation to use. This is not very hard to do. In the next sessions, we're gonna do a practice class. Okay, we're gonna do some calculation together, and I will show you how we can decide which set of equation to calculate the confidence interval. Okay, so that's the end for this lecture, and we finished chapter 5.